Welcome to EMAG and welcome to our webinar, Laser Cleaning, a Powerful Tool. Today we have prepared a webinar for you where we want to introduce exciting technology which is already a number of years existing and being used, and we would like to present that technology to you and see if there are more opportunities to use the advantages of this exciting process. Before we jump in, you are most welcome to raise questions, to ask questions. We will try to answer them right away. So our back office, they will collect them, bring them on the screen, and if it fits in, we will answer them right away. So please use that opportunity and ask whatever you would like to ask about laser cleaning. This way. Okay, what do we want to address today? First of all, I will give you a brief introduction. What are we talking about? I will try to figure out the advantages of this process, laser cleaning. After that, we will dive a little bit deeper into the principle of operation. We will address the question, or we will raise the question, what means clean? It's not that easy to answer that. And last but not least, we want to introduce to you an EMAG product, an implementation of this process, the EMAG LC4, together with the Easy Clean software. Before we start, we would also like to introduce ourselves. Together with me is my colleague, Mrs. Dr. Melanie Mangang. Dr. Mangang is an expert in laser processing. She works in the EMAG LaserTec lab, in the laser application lab. And she's an expert for pulsed laser processing, for microprocessing. Dr. Mangang holds a PhD degree from Karlsruhe Institute of Technology, one of the famous German technical universities, and she's the real expert. Myself, I'm Andreas Motz. I'm the CEO of EMAG LaserTec. Part cleaning. In industrial production, many manufacturing or even assembly processes require clean parts. You find on the process sheets, on drawings, you find specifications such as free of oil, free of chips, dry, combinations of all these requirements, sometimes a little bit more detailed. For example, you have specifications for the maximum surface tension or similar specifications. A lot can happen. Typical processes that require a specific part quality is welding, is gluing, any type of coating processes, paints, zinc phosphate coating, you name it, or assembly operations may require clean parts. So a lot of requirements, electrical, sometimes it's required to have a decoated area or a non-isolating area on a surface as a ground pad or so. So a lot of requirements, different requirements. On the other hand, real parts, they have been cut using a coolant, have been ground using oil, have been formed using some grease and oil, etc. The parts may have been manufactured in an outside facility coming from a sub-supplier and have a corrosion protections on the surface, which is not suitable for the downstream process. Other parts are non-corrosion protected and therefore a little bit oxidized, you name it. A huge variety of input conditions, let's say, which may not be acceptable for the downstream process, and therefore part cleaning is required. Unfortunately, cleaning is not considered to be a value-adding process. It's a must-have. It has to be, on one hand, it has to be as cheap as possible, but it may be most relevant for the downstream process, and therefore it's worth to look a little bit deeper into that and find the right cleaning technology to fulfill both quality requirements as well as economical constraints. If we walk through a shop, we see a lot of technologies that are being used for part cleaning, excuse me, not for laser cleaning, but for part cleaning. A lot of processes have been developed over the years, are being used over the years. If you want to categorize them a little bit, then you can define three major categories. One is chemical technologies, such as washing. You may, or you find a lot of mechanical processes, if it's brushing, grinding. Ultrasonic cleaning is also a mechanical process. You may find CO2 snow blasting, or you may find physical processes such as plasma treatment, plasma cleaning, or laser cleaning. And in many real applications, you find combinations of these categories. For example, high pressure washing is a process that combines a chemical process with a mechanical process. Today, we want to look a little bit closer to the laser cleaning. We at EMAG LaserTec, we use this technology for almost more than 10 years. And we find it's a very modern and innovative process with a lot of advantages. And therefore, it's worth to look a little bit closer to this. What are these advantages? First of all, I would like to mention the quality. Laser cleaning has the ability to deliver excellent surface quality, but it has also the ability to deliver that all the time. So you have an extremely high process capability. You have a very constant surface quality. This is, from our standpoint, a most important feature with respect to the following operations. Laser cleaning has the ability for local cleaning or decoating in a geometrically defined area, which is sometimes mandatory. I will come to this later, and is a nice feature. Laser cleaning does not require part drying. Why do I mention this? In many cases, an alternative to laser cleaning, the older and more established process is conventional washing in a 3-zone washer. Wash, rinse, dry. And the lack of dryness is, in many cases, the root cause for problems in the following downstream process. If it's gluing, if it's coating, if it's welding. If you don't have really dry parts, then you run into trouble, and this happens in real life very often. And laser cleaning is a dry process, and therefore we do not have that issue. Laser cleaning is also nice in terms of line integration and automatization can be integrated very nice. The maintenance is very little compared to a washer, for example, and it's an economical solution in terms of running cost, and it's also affordable, I would say. Here we have a video of a real life example. This is a welding cell for powertrain components made by EMAG LaserTec, and here you see the cleaning operations. Parts are fed in using a gantry loader. It places the individual parts. By the way, this is an intermediate shaft or an E-drive system. Places them, the index table shuttles in, and the process starts right away. On the lower right, you see the HMI screen where we visualize the process. There's not so much to see. This is the speed is it's live. So this is a very fast process, and that was it. Very clean, almost no splatters, so quite interesting. Done. Now I would like to come to the point, what is all behind this? And therefore, I hand over to my colleague. She will go into the details and explain the process to you and ask the question, what's clean? But before I do that, I got a sign. There is a question from the audience. I would answer that myself before I hand over. The question is, plasma cleaning or carbon dioxide cleaning is less expensive than laser cleaning. Why not plasma or about CO2 snow? Okay, that's a good question. Plasma cleaning. Plasma cleaning uses a plasma jet to clean the surface. We looked in this process a while ago when we were deciding which route to follow. Plasma cleaning is very capable. It's relatively simple, and you can use it. It works very nice for example, an oil film or some corrosion inhibitors on a metallic part surface. This works pretty well. It doesn't work if you sink for oxides, if you sink for any paintings. These are the limitations. The laser is more aggressive, and so the process has some limitations. CO2 snow, what is that? It uses, in German it's Trockeneis, dry ice. At the end of the day, it's carbon dioxide crystals, very cold carbon dioxide crystals. They are like a shot blasting. They are accelerated and hit the surface. This process is nice, for example, for removal of paintings, coatings. The good news is the carbon dioxide will vaporize. So after the process, you have only the dirt material, not a mixture of blasting material and painting, for example. So that's good. When we tested this process, we found out it's not so nice if you have, for example, a coolant film on the oily films on the workpiece surface. You don't get the quality that is required, let's say, for painting, for gluing, for sealing, for welding. It didn't fit with our quality expectations, so the downstream process was not that good as it should be, and therefore we went away from carbon dioxide snow. I have to say, carbon dioxide snow, the equipment is not that expensive, but the running cost is high. You need the carbon dioxide, and for the equipment, the process is very noisy. So therefore, you need to consider some noise protection in your shop. So at the end of the day, the capex the difference, the investment cost is not that such a big difference. Okay, I hope this answers the questions. And now, again, I would like to hand over to my colleague, Dr. Mangang. The stage is yours.
Thank you, Dr. Mutz. So you heard about that laser cleaning is a very nice tool for process different things, and why it is such a nice tool and why you can process different things. I want to explain by how laser cleaning is working. Laser cleaning, as the word says, use laser beam for removal of this contamination layer. This contamination layer could be either the same material as the part or different material as the part, and this is removed by the laser beam. Mostly for laser cleaning, you have different material as contamination, like liquid contamination from corrosion inhibitors or phosphate layers. So since the laser beam is just removing the contamination, it is necessary to have also a suction or extraction unit to really remove the removed particles from the interaction area. Let's have a closer look. The laser beam is created by a laser system, more precisely a pulsed laser system. Why a pulsed laser system? Since you use the pulsed laser with a really short pulses, you can generate high peak powers. So with the high peak powers, you can remove different kind of materials quite good. And also because it's really a short interaction time from laser beam to material, so short, like 1/1,000,000th of seconds of really interaction time. This means that the material which you do not want to remove, which should stay the same, will not be really influenced by the laser beam. Then you have a mirror system which moves the laser beam over the surface of the component. So everywhere you want to, you can move the laser beam. And then you have this, you have the parameters of the laser beam. You have the parameters of moving the laser beam over the surface. And you can also move the component underneath the laser beam. So you have various parameters which need to play together to have at least the goal, to realize the goal, to have a good surface quality. And always taking into account the process time, because the cost should also be minimized with this process. Let's have a closer look into the interaction zone between laser beam and sample. So you have, it looks like a little bit complicated. You have a lot of different zones which are happening during the laser process, but it's not that complicated as it looks like. If we go through it in detail, so we have the laser beam hitting the surface. The laser beam will partly transmit it, partly reflect it, and partly absorbed by the material. The absorbed part of the laser beam will increase the temperature of the material. And with more interaction time, the temperature will rise. You get a melting of the material, and later on you get also vaporization. So you remove the material at least away from the surface. But this sounds very slow when I explain it. The time between hitting the surface and vaporization is really slow, because it's really fast. I'm sorry, not slow, because the pulse durations are really high. They are really slow. You had only nanoseconds pulses, thus the interaction time between laser beam and surface is like just millions of seconds, as I already said. And thus the time between hitting the surface and removing the material is also a millionth of time. So it's really fast. And the reason why you don't hurt the surface of the sample, not that much. So since you have a lot of things you take into account, you have the laser beam. The laser beam has, for example, a certain wavelength. The wavelength will be absorbed differently by the material, if it's steel or if it's ceramics. So you have to take into account the laser parameters. The component has its influence because it has a certain reflectivity. It has a certain heat diffusion into the material. The top layer you want to remove has an influence. It could be also reflective or transmitting. The amount on it is also you take into account by the laser process. At least there are a lot of parameters, but the goal should be to remove your top layer, your contamination, to have a good quality at least, and also the reduced process time, also always taking into account. But for laser cleaning, it's quite hard to say when is it clean? What is clean? So you have different methods to check. So it's only an indirect method to measure the cleanliness of a surface. You can use, for example, the contact angle measurement. So you put a drop on the surface, and for a contaminated surface, you have more spreading of the angle, thus a low contact angle. And if you laser clean it afterwards, you get a high contact angle, you get an increase of the surface energy, and the drop looks more like a ball. Similar and quite easy to handle is the testing. You use different surface energies with which you compare the surfaces. And as I said, contaminated is a low surface energy, and laser cleaned is a high surface energy. Also, the roughness is quite important because you don't want to hit the surface that much. So you check also if the roughness is still okay. Sometimes you also want to increase the roughness because you have following processes which need an increased roughness. At least the laser cleanliness is a value which also is influenced by the following processes. So sometimes it is important or it is not important to have a roughness or not. You can also use visual inspection by eyes or by incident light microscopy or in more detail electron microscopy. This works quite good, for example, for phosphate layers. And you can use fluorescence measurements. They work really nicely for liquid contaminations. So when there's a liquid on the surface, it starts to fluoresce under this system. And the more liquid is on it, the more fluorescence will happen, and the more higher the value will be. We have usually more liquid contaminations on our surface, thus we use the testing or the fluorescence measurements. The testings, as I said, they are really easy to handle, and you can nearly measure everywhere with these testings. That's quite nice. For fluorescence measurements, you have a little bit problems since you have a certain size of this handheld system, but you can also automate it in a certain range, and you get always a measurement value, so you can compare it over a certain time, and it's always the same. How this looks like when you laser clean, and what means clean, and what the surface will be influenced. We did a basic research. We had some samples, put some corrosion inhibitor on it, and we laser cleaned it. And you see, we checked this with fluorescence measurements. And for the contaminated ones, you have this high value because you have a lot of liquid on it, which fluoresces a lot. And after the laser cleaning, the fluorescence value is really low, so also below a value of 1. We compared it also to hand-cleaned surfaces with isopropanol, and this is also a low value, but you can also see this is a low value underneath 6, and the one for the laser cleaning are underneath 1. So it depends really on your following process. If it might be 5 enough for a laser clean surface, it might be 15 enough for a laser clean surface. Depends on the process afterwards, if it's okay or if it's fine with also some more contamination on it. And what you can also see for the fluorescence for the laser clean surface, you have really a constant value. It's over the whole surface you measure, you have the same, almost the same. But taking into account not only this cleanliness, also the roughness, because you don't want to hurt the surface that much. We check also the RA value, so with higher power for sure, sorry, with higher power for sure, you get a higher roughness, and with decreasing power, you have a lower roughness. You saw at the beginning slide that you have for all a clean surface, but at least to have a good surface, you use more, in this case, lower or average power. And the influence of laser cleaning on the limits of laser cleaning, or what can be laser cleaned, is now saying Dr. Motz a little bit more in detail. So I hand over to Dr. Motz.
Thank you, Dr. Mangang. Meanwhile, we received another question. Let me read it. Can laser cleaning be used for removing thin coating layers? This is the perfect application for laser cleaning, I would say. So I didn't mention that before, but we have a laser application lab in EMAG, and Dr. Mangang welcomes you if you want to do some tests and check out whether that process is feasible or suitable for your requirement. You're most welcome to get in touch with EMAG, and we will sit together and see if we can solve your problem. And she is waiting for your inquiries. So, okay. As we announced it, we would like to talk a little bit about process selection. First of all, I want to make a clear statement. Laser cleaning is not a one-by-one replacement for conventional washers. It's a physical process. It's another process, and when you have to choose a part cleaning process, then you need to consider a big variety of different parameters for your decision. So if you want to categorize these parameters, you have to think about workpiece properties. I'll explain that more in detail in a second. So type of contamination, let's say as an input condition, and required part condition after the cleaning process, of course, is an important factor. There may be some special requirements to the workpiece. Though this is more from the technology side, but you also need to think about the manufacturing side, integration into the bill of process, and of course about economical aspects and the running cost, etc. Okay, let's go a little bit deeper into this. Workpiece-related criteria. If we talk about materials, laser cleaning can clean almost everything. It's enormous. You have seen that in the charts. You have a huge variety of parameters you can modify, and therefore you can adapt this process to a huge variety of materials. If it's metal, if it's plastics, if it's ceramics, if it's glass, if it's organic, almost everything seems to be possible. If it comes to washing, I would say typical industrial materials, cast iron is hard to wash. We see that. Sinter metals is even worse because of the porosity. There is some oil always sitting in the material, and you wash, but it doesn't get clean. So from the material standpoint, I see a clear plus for the laser cleaning. Geometry, laser cleaning is a little bit demanding in that we need access for the laser beam. So inner contours, bores with a certain aspect ratio are not possible. These difficult geometries cause also problems in a conventional washer, but usually you find a solution. Not always, but usually you do. So I would say washing has some plus more points than the laser cleaning at this side. Surface. With laser cleaning, you have seen that in the slides. You can adjust the process to make sure that you do not hurt the surface. You can also establish, for example, a defined roughness in the workpiece surface, which can be an advantage if you think for coating processes, thermal spraying, for example, you name it. So in washing, usually you have no impact except some corrosion problems which may occur. And part temperature is also different. Laser cleaning is almost a cold process, no significant warming. Washing, depending on the liquid, depending on the chemistry, process temperature can be 60 centigrade, 75 centigrade sometimes, which is 170 Fahrenheit. I hope I calculated that right, which can raise a problem. Now I got another question. I think I'll forward this to Dr. Mangang. I'll read it. What about the minimum maximum distance and the angle between the laser head and the part to be cleaned? Okay. Sometimes geometries don't allow the laser head to reach the correct focus distance and or angle of incidence. Dr. Mangang, please.
So regarding the MinMax distance, this depends on your scan system and your objective. This defines at least the distance. So you can have a look on this and choose especially one for this. The angle is also, this is what will be, the laser beam must be absorbed by the surface. So you need to take into account the minimum angle is that what will be absorbed at least by the surface. So for metals, it's I think about 20 degrees for which you need minimum to have that the laser beam will be absorbed by the surface. So you're right, the geometry is, you have to take a look on the geometry, but you have also a certain Rayleigh distance for the lasers, especially the pulsed laser systems. They have a quite good beam quality, so you have a bigger area where you really work in the focus, on the focal area. So this is the so-called Rayleigh distance, so you don't need to be exactly in the focus.
I think we can compensate for some millimeters, 2, 3, 4 millimeters, depends on the optics, the processing optics, and the angle of incidence has, of course, an impact on the effectivity of the process. So if you have a non-optimal angle, you can compensate by reducing the feed rate. So you have quite some options to play with, a window, let's say. And
you can also use additional mirrors also to change the focal position afterwards.
Okay, the type of contamination is an important thing. Laser cleaning, this was the previous question, thin coatings. This is a perfect application for laser cleaning. We suggest for thinner layers, it's super. Thicker layers may cause some issues. In washing, oil, cooling lubricants, stuff like this can be washed away. But what we experienced in the past is that some MQL coolants raise problems. This is caused by their chemistry. If it comes to chips and particles, this is definitely a no-go for laser cleaning. It's also nasty for washing operations, but you can have a washer which you need some measures like mechanical filters to protect the pumps, etc. But it's possible. For laser cleaning, chips are definitely a no-go. Coatings such as paintings, zinc phosphate coating, powder coating, stuff like this is the laser is not interested in this. It's very suitable. It's biting away all this. Washing is not a suitable process for this type of contamination. So when I answered that question about the plasma coating and CO2 coating, laser cleaning is very capable for this type of contamination. And also oxides, rust, it's very suitable, I know, in aerospace industry for gluing aluminum. It's a standard process to remove the aluminum oxides by laser cleaning, meanwhile, to have a constant quality. Now, there is another question. Dr. Mangang, do you want to answer that? The question is, for inner profile, can you use mirror to let the laser beam to reach the surface?
There are special optics which can go into some holes and the laser beam is just changed by a mirror. That's true. It depends, but on the opening size where you want to go into. There's also a minimum size where it's not possible anymore. But this, we need to check for detail how big the size is.
This needs to be answered case by case. So the bore diameter and the aspect ratio, the depth of the bore is critical. It's nasty because the mirror is very close to the process, and you need to protect your optics, and so it has limitations. But we have done that, yes. But we do not love it. Okay. Special requirements coming from the workpiece. Decoating of defined areas, cleaning of defined areas. I mentioned that already in the beginning when I talked about the advantages of that process. The travel of the beam is completely CNC controlled. And that is an interesting option for some applications. For washing, per definition, it's not possible. But for the laser, we use that. We had a project where we had to clean a aluminum case for an electrical motor, and the final operation was a sealing operation, and to remove the oxide layer, we removed it with laser cleaning, and it was a non-round geometry, so we had a XY coordinate system to clean the path for the sealant, the shape for the sealant. So this is a perfect application for laser cleaning. That is also true for pre-assembled components. You cannot wash them because you never would be able to clean and to dry them. So these are specific advantages of the cleaning process because it's so local. This has also an impact if you think about rust or corrosion inhibited parts, corrosion protections, because you remove only in the process zone for the downstream process, let's say for gluing or for welding, the rest of the part remains untouched. If you have a corrosion protection there, you will have it also after that gluing or welding process. This can be an advantage depending on the local action, and you retain this. And dryness, I addressed this already in the beginning. This is absolutely no issue with laser cleaning, but it can be a nightmare with a washer. Integration, both technologies can be integrated into manufacturing lines. Per definition, laser cleaning is a serial one-piece flow process. This has some advantages. You can bring it very close to the downstream process. You clean and you weld, you clean and you glue. This is a big advantage from our standpoint. Washing is either a batch process or an inline process. So both can be automated, but we see a more modern approach for the laser cleaning. The footprint, there's a writing error, is very small compared to a washer, and the emissions, you have some fume that needs to be sucked away, and you need also filtration. On the other side, washer, it creates heat, noise, and you have to remove the used liquid from time to time. Of course, it's because it's laser technology, you will need a laser safety officer, but today this is no big deal. And on the other hand, for washers, other environmental regulations apply, so pros and cons on both sides. Flexibility, also a good question, because laser cleaning is a programmed path. You have a lot of flexibility. Fixture requirements, yes, you need to locate the workpiece, as Dr. Mangang just said when she asked the question. I got a new question, but I shift that back a little bit. Generally speaking, you should present the part with an accuracy of 1 millimeter, which is not super precise tooling. On the other hand, a washer, if you have bulk material, no tooling, this is best, of course. But if you use, for example, if you weld powertrain components and run them through a washer, and you don't want to protect your gears, you will use typically pallet conveyor systems. And to make a pallet conveyor system capable to run through a wet washer, the pallets are demanding, I would say, and costly. So there you have a huge variety of costs. There is no general answer. And C programming is required for the laser cleaning. Yes, this is flexible, but you need to do something. It's not required for washing. And if it comes to technology, I think in the slides that you saw the huge number of parameters that have an impact, that can be changed, but they need to be set up. I cannot tell you, is this good news or is it bad news? It's good news because it allows you to adjust or to adapt this laser cleaning process to a lot of requirements. It's bad news because you have to manage all these parameters, and we have an answer for this to make it which is named Easy Clean. It's a software developed by EMAG, and I come to this in one of my next slides. On the other hand, washing is it's not that complicated. Of course, you have to select the right washing liquid, you have to maintain it, you have to monitor it, and temperature control is not that complicated, and time, and that's it. So I would say from the technological standpoint, yes, you have more to do up front, but we have answers for this, how to reduce this. Meanwhile, we got another question. Would you like to answer that? Are you able to clean hose of 50 millimeter all through, 100 millimeter in depth? I think from one side it's tough,
I think also.
This could be a solution for what Dr. Mangang just mentioned, having an ID process head with an additional mirror. It's worth to look at it, I would say.
Yeah.
It's not off the shelf, but it's worth to look at it. Okay, last slide, criteria for process selection, cost. Running, this is from manufacturing people, this should be the first slide. The running cost is very little. The connected load is very little compared to a washer. They have usually typical washer, 100 kVA connected load, and sometimes far more than that. So they are a big waste of energy. Washers are a big waste of energy. Their ecological footprint is not very nice. Maintenance, here you have some components that need to be replaced from time to time. It depends a little bit if you bring in a lot of oil in the system. If you have a lot of oil on the surface, then the machine gets dirty. You need to clean it more open or change the protective window from time to time. On the other hand, with a washer, you need to maintain your liquids. You have filters, etc. So generally speaking, the maintenance cost, the running cost is far below. If it comes to CapEx, if it comes to investment cost, I would say compared to a quality washer, laser cleaning is competitive for sure. It is, if it works. But at this we looked indeed. This about process selection. This brings me to my last point. I said we want to introduce you to a real EMAG product. It's EMAG LC4. As I said earlier, we have done a lot of stations as a part of manufacturing systems. We use the cleaning technologies for more than 10 years. The LC4 is more a standard approach. In the video, you saw it as an integrated machine. This simply means that the front loading gate is dismantled and the index table is accessible for robot, for gantry, stuff like this, automation components. The size, it's suitable for workpieces up to 200, but we have developed also a bigger version. We use a 200-watt pulsed laser. It's a small 19-inch rack which is integrated in the electrical cabinet, so nothing to see. And as I said, standalone and automated versions are available, some options. Before I come to a video, here are some details. So you have all the components that are required for this process. Oops, this was a little bit fast. And now I would like to come back to technology and how can you operate that. I think Dr. Mangang clearly presented to you, there is a huge variety of parameters. You have laser parameters, pulse parameters, you name it. You have scanning parameters. I can tell you the scanning strategy, that means how you move the laser beam over the workpiece has a big impact on the quality and also on the productivity, on the aerial rate. So a lot of parameters. Then you have the workpieces and it's far too much for a machine tool operator. And therefore we developed the software, it's named Easy Clean, EMAG Easy Clean. And the idea behind this software is to bring everything together, easy to use, and it allows an operator to focus on typical technological parameters, workpiece parameters such as part diameter, cleaning track width, things like this. Most important technological parameter is the number of laser pulses per area, per square millimeter or per square centimeter. Things like this, typical parameters that an operator can easily handle. But you have also an expert mode, which allows you to modify all these things and find an optimized parameter set for your specific application. Usually the system comes with a technology table in the back where we have predefined parameter sets that need only to be adapted to the specific workpiece. And we feel it's a good tool to make that sophisticated process to increase the usability, let's call it like this. So this is Easy Clean, and I have another slide. Here you see only a circular point which is moving over the workpiece. You have also an option to use the equipment as a marking device. This was developed a while ago based on customer demands. He said, oh, I have that, can I use it? Can I create a data matrix code at that time? We developed that. Meanwhile, we have made the next steps, especially if it's for non-round geometries. We can program it very simple, like a 2.5D milling machine. You only program the XY path in G code, so very simple. You can. I think it's also feasible to use some 2D CAD systems. It's a very flexible tool. So you have a huge variety of options to use that laser cleaning, or in this case, laser marking technology as well. And last but not least, a short video, but this is the LC4, very nice, compact machine. Everything is on board except the fume extraction. Manual loading gate, the operator or robot places the workpieces there. The index table swivels, and here we go. And you see the fume extraction, which is an important part, but it's a simple thing for these round components. That was it. I would like to thank the audience very much for the time you gave to us. Well, before I close, I have another question. It would be possible to know the range of temperature reached on the laser cleaned surface. You can answer that. I see. It's cold. It remains like it was.
Yeah.
There's no impact. This is a crazy thing. I think Dr. Mangan mentioned that we shoot only very fast and short pulses on the workpiece surface. The time is below 1 millionth of a second. It's 0.1 of a millionth of a second. This is almost nothing. So the interaction time is very, very short. We repeat this 200,000 times per second. Yes, but this is exactly the advantage of short pulse lasers. You can have a cold process. So you do not need to wear gloves if you load, unload manually. You shouldn't touch the surface with your fingers to avoid any contamination. Yes. And I got another question. I think, yes, I can answer that. Okay. Obviously, somebody's already thinking about using laser cleaning. The question is, our welding cell is equipped with a TrueDisc 4002 with one free fiber exit. Can we connect the laser cleaning cell to this laser? I'm very sorry, this is not possible. Why is that? I just explained we have pulsed lasers. They shoot only small pulses, like a needle, on the workpiece surface. The TrueDisc 4002 that this auditor is asking for, this is, we know this laser very well. This is a disc laser, a solid state laser made by company Trumpf with a power of 4,000 watt, 4 kilowatt, so far more than we need. But this is a so-called constant wave laser. The laser radiation is continuously there, but no pulses. We need short but very intense pulses to have that ablation process. And therefore, I have to say, sorry, but we cannot use this. But the pulsed laser, it's only a 19-inch device, and it's completely integrated. And another question, does EMAG offer cleaning tests? Yes.
For sure.
This is why we are here.
Yeah, that's true.
I think I addressed this already. Dr. Mangang is waiting for you.
Yeah, we are looking for further
exciting applications.
Yeah.
Yeah. And for this, I need to check, was that the last? I think this was the last question, yeah, okay. If you want to do a test, make a feasibility study, you're welcome to do so. EMAG has the ability in our laser application lab, and we are waiting for you. Please do not hesitate to contact us. You have our contact data, and you're welcome to send us or to discuss your inquiry, your project, to discuss your project with us, and we will try to elaborate the best solution for your needs. I think we are done. I would like to thank you, to thank the audience for the time you gave us, and let's stay in touch, and we are waiting for your inquiries. Thank you so much. Goodbye.
Thank you.